December 1941. The telegram trembled in David Marshall Williams's calloused hands, its words blurring as smoke from his workshop forge curled through the North Carolina air. Pearl Harbor had fallen just days ago. America's arsenals were screaming for weapons, and weapons that could stem the tide of Axis aggression. But the 31-year-old convict-turned-inventor knew his creation, the one he'd obsessed over for 13 years, would be laughed out of every military procurement office in Washington. He'd already rejected it twice before. Williams stood alone in his cluttered Godwin workshop, surrounded by half-disassembled rifles, oil-stained blueprints, and the mechanical ghosts of 1,000 failed experiments. His neighbors called him Carbine Williams behind his back, though the kinder ones simply muttered about the strange hermit who'd served time for killing a deputy during a moonshine raid back in 21. What they didn't understand, what the brass-button generals 500 miles north couldn't comprehend, was that this weathered welder had solved a problem that had vexed firearms designers since the American Civil War. The rifle propped against his workbench looked deceivingly simple. It's just under 3 feet long, weighing a mere 5.5 pounds. It seemed almost toy-like compared to the 9-pound M1903 Springfield that American doughboys had carried through the trenches of the Great War, but nestled inside its walnut stock was Williams's secret, a short-stroke gas piston system so elegant, so revolutionary that it would eventually transform modern warfare itself. Williams had conceived this mechanism during the darkest period of his life behind the stone walls of Caledonia State Prison Farm, where he'd been sentenced to 30 years for second-degree murder, according to historical records maintained by the North Carolina Department of Corrections. Prison Superintendent H.T. Peoples had recognized something extraordinary in the volatile young convict. Instead of breaking rocks, Williams had been allowed to establish a small machine shop, ostensibly to repair farm equipment. In that cramped space, surrounded by guards and the desperate, he'd sketched designs on smuggled paper and carved prototype parts from scrap metal. The genius of his invention lay in what it didn't do. Traditional automatic weapons relied on complex, heavy mechanisms to absorb the explosive force of burning gunpowder. Williams's short-stroke piston captured just enough gas from the fired cartridge to cycle the action a brief, controlled tap rather than the prolonged push that complicated other designs. The result was a rifle that could fire semi-automatically with minimal recoil, fewer moving parts, and a simplicity that made it both reliable and quick to manufacture. But simplicity had never impressed military procurement boards. They wanted proven designs, not the fever dreams of an ex-convict who'd taught himself engineering in a prison cell. Winchester Repeating Arms had examined Williams's patents in 38 and passed. The Army Ordnance Department had dismissed him in 40. Now, the Japanese forces advancing across the Pacific and German U-boats prowling the Atlantic, Williams faced his final chance to prove that madness and genius often share the same workshop. He reached for the telephone, knowing the conversation ahead would require every ounce of the stubbornness that had kept him live in prison and sane through years of rejection. January 1942. Colonel Rene Studler of Army Ordnance stood before a conference table buried under 43 different rifle submissions, each one claiming to be America's salvation. His headache had persisted for 6 days straight, pounding in rhythm with the war production quotas that seemed to grow more impossible by the hour. The United States needed to arm 15 million men within 3 years, a logistical nightmare that made the Great War mobilization look like a county fair shooting competition. The problem wasn't just quantity. American soldiers were fighting in jungles, deserts, frozen mountains, and island beaches simultaneously. They needed a weapon lighter than the Springfield rifle for jungle warfare, more reliable than the temperamental M19 Garand for beach assaults, and simpler to produce than either. The War Production Board had calculated that manufacturing traditional rifles consumed approximately 12 hours of skilled labor per weapon. With current designs, meeting military demand would require commandeering every machine shop from Boston to San Diego. Studler's eyes burned as he reviewed the day's rejections. The Johnson rifle too complex. The Rising gun too delicate. The various foreign designs too dependent on overseas patents and manufacturing techniques. Each submission represented months of development work and thousands of dollars in prototype costs. Yet none solved the fundamental equation: how to build millions of rifles quickly without sacrificing reliability. Winchester's chief engineer, Edwin Pugsley, had been working secretly on his own design since mid-41, refining a lightweight carbine intended for support troops, vehicle crews, and paratroopers. His design showed promise, but it lacked a reliable operating system. The corroborated mechanisms he'd tested were either too heavy or too prone to fouling. As documented in Winchester Company archives, Pugsley had burned through 17 different action designs in 6 months, each one failing some critical test of durability or simplicity. It was during this period of mounting desperation that Jonathan Ed Browning, son of the legendary firearms designer John Browning, mentioned Williams's name during a procurement meeting. Browning had heard rumors about the short-stroke piston system, through industry channels whispers about a self-taught designerhood. Developed something revolutionary while serving time for killing a man. The story sounded like pulp fiction, but Studler had learned that desperate times demanded investigating even the most unlikely leads. The call to Williams's Godwin workshop went through on January 15th. Williams, expecting another rejection, answered with characteristic bluntness. He had a working prototype. He had drawings. He had test data showing his system could function reliably after firing thousands of rounds without cleaning. When Studler asked about manufacturing complexity, Williams delivered the answer that would change everything. His design required 30% fewer machining operations than comparable systems. 30%. In the arithmetic of total war, that number represented millions of man-hours that could be redirected to building tanks, aircraft, ships, and all the other machinery of modern conflict. Studler requested an immediate demonstration. Williams, suspicious but desperate for vindication, agreed to travel to Washington with his prototype. The train journey north gave Williams time to doubt himself. His hands, scarred from years of forge work and machine accidents, trembled slightly as he checked and rechecked the rifle case beside him. He'd been dismissed as a criminal, a madman, a tinkerer who didn't understand real engineering. Now he was carrying a weapon that weighed 5.5 pounds against the backdrop of a war that would be measured in tens of millions of lives. January 23rd, 1942. Snow fell on the Aberdeen Proving Ground in Maryland as Williams unpacked his rifle. Under the skeptical gaze of 15 military officers and engineers, the testing range stretched before them a bleak landscape of frozen earth, sandbag berms and wooden targets that had absorbed bullets from every experimental weapon the War Department could conjure. This would be Williams's trial by fire, and everyone present knew that millions of American lives might depend on what happened in the next few hours. Major Julian Hatcher, one of the Army's most respected ordnance experts, approached the table where Williams was assembling his rifle. Hatcher had personally evaluated hundreds of firearms designs over his 30-year career, and his technical reports could make or destroy a weapon's prospects. He picked up Williams's prototype, his experienced hands immediately noting its unusual balance and surprisingly light weight. According to Hatcher's later published memoir, The Book of the Garand, he'd expected another overcomplicated contraption from an amateur designer. What he held felt different, purposeful, elegant, almost organic in how its components integrated. Williams explained his short-stroke piston system in the clipped, canonical language of a self-taught engineer who'd learned precision through trial and error. When gas pressure from the fired cartridge reached a specific threshold, a small piston tapped the operating rod just enough to unlock the bolt and extract the spent casing. The piston immediately returned to its resting position, isolated from the mechanism's moving parts. This separation meant less fouling, less friction, and fewer components that could break under combat stress. The officers exchanged glances. They'd heard promising explanations before, usually from designers whose weapons seized up after 50 rounds, or whose simple mechanisms required jeweler's precision to manufacture. Theories meant nothing on a proving ground. Hatcher loaded a 30-round magazine and handed the rifle back to Williams. The test would be brutal, 300 rounds fired as quickly as possible, followed by a mud bath and another 100 rounds without cleaning. Williams's first shot cracked across the frozen range at exactly 900 hours. He fired methodically, letting the rifle's semi-automatic action cycle with mechanical precision. Spent brass arced through the falling snow, glinting briefly before disappearing into the white-covered ground. At round 50, Hatcher inspected the action. Clean cycling, no signs of unusual wear. At round 100, 2 other engineers examined the gas system, still functioning perfectly. By round 200, whispers rippled through the observation group. By round 300, Colonel Studler was making rapid calculations on a notepad. Then came the mud test. An assistant dumped the rifle into a barrel of thick, squeezing sludge mixed with sand and gravel, the kind of foul mixture that soldiers would encounter in Pacific jungles and North African deserts. Williams retrieved the weapon, made no attempt to clean it, loaded another magazine, and resumed firing. The rifle coughed once, ejected a mud-packed casing, and continued functioning. Officers who'd remained skeptical now leaned forward, forgetting military decorum in their eagerness to see what happened next. According to contemporary testing records preserved at the Aberdeen Proving Ground archives, Williams's rifle completed the 400-round test with only 2 minor stoppages, both caused by defective ammunition, rather than mechanical failure. February 1942. Edwin Pugsley sat in Winchester's New Haven, Connecticut boardroom, reviewing specifications for a weapon that didn't quite work. His lightweight carbine design showed tremendous promise. The Army desperately needed exactly what he'd conceived. But the operating system remained Winchester's Achilles heel. Every gas-operated action he'd tested proved either too complex for rapid mass production or too fragile for combat reliability. The pressure from Army ordnance was becoming unbearable. Winchester, one of America's most storied firearms manufacturers, faced the humiliating possibility of losing the war's most important rifle contract. Then Colonel Studler's report landed on his desk. 5 pages of technical evaluation, accompanied by high-speed photography sequences showing Williams's short-stroke piston in action. Pugsley read the document 3 times, his engineering mind immediately grasping what Williams had achieved. The system was brilliant not because it was complicated, but because it was almost absurdly simple. Where other designers had tried to harness the full force of propellant gases, Williams had recognized that a brief controlled tap could accomplish everything necessary. It was the difference between sledgehammering a nail and using a precision strike. But Pugsley faced a delicate problem. Williams was notoriously difficult, protective of his designs to the point of paranoia after years of rejection. Winchester needed his operating system to save their carbine project, yet they couldn't simply appropriate his patents without negotiation. The company's legal team had examined. Williams's intellectual property had been filing and defending patents since his release from prison in 1939, building an impregnable fortress around his innovations. The meeting between Williams and Winchester executives occurred on February 9th in New Haven, according to company records documented in Historian. Herbert House's book Winchester Repeating Arms Company. The session nearly collapsed within the first hour. Williams distrusted corporate bureaucracy, having watched larger companies dismiss his work for years. Winchester executives, accustomed to dealing with conventional inventors, struggled to communicate with the volatile ex-convict who spoke in machine shop vernacular rather than business language. Pugsley finally broke the impasse by doing something unusual. He showed Williams complete respect as a fellow engineer. He spread Winchester's carbine blueprints across the conference table and admitted candidly that their operating system was inadequate. The rifle's ergonomics were excellent, manufacturing approach was sound. But without a reliable action, everything else was worthless. He asked Williams not as a supplicant to a patent holder, but as one designer to another. Would Williams's system work in Winchester's carbine? Williams studied the drawings for 2 hours without speaking, his calloused fingers tracing barrel dimensions and stock configurations. His mind performed calculations that would have required pages of mathematical proofs from a university-trained engineer. Finally, he looked up and delivered his assessment. Yes, his short-stroke piston system could be integrated into Winchester's design, but he demanded conditions. He would supervise the adaptation. Personally, he would maintain control over critical specifications. Winchester would acknowledge his contribution prominently. The negotiations consumed 3 weeks. Winchester's lawyers drafted contract language that protected both Williams's patents and the company's manufacturing flexibility. The agreement reached in early March represented an unusual hybrid. Winchester would produce the carbine using their manufacturing infrastructure and basic design. But Williams's patented short-stroke gas piston system would form the weapon's mechanical heart. More importantly, Williams would relocate temporarily to New Haven to oversee the integration process. This partnership between the corporate giant and the self-taught convict inventor would prove to be one of the war's most consequential collaborations. Winchester gained the reliable operating system that made their carbine viable. Williams gained the manufacturing capability and military connections he'd never possessed working alone. April 1942. Winchester's massive New Haven factory floor roared with activity as the first production models of what would become the M1 carbine began rolling off assembly lines. The transformation from Pugsley's flawed prototype to a battle-ready weapon had consumed only 8 weeks of development timeline that would have been considered impossible in peacetime. Williams stood on the factory floor watching drill presses and milling machines shape steel into the components he'd envisioned years earlier in a prison cell, and permitted himself a rare moment of satisfaction. The M1 carbine represented more than just Williams's vindication. It embodied a revolution in military manufacturing philosophy. Traditional rifle production had relied heavily on skilled machinists performing complex operations, hand-fitting parts, precision grinding, individual adjustments. The M1's design philosophy, enhanced by Williams's simplified operating system, embraced what would later be called parts interchangeability at scale. Components were engineered to function together within looser tolerances, eliminating the need for expert fitting and adjustment. As reported in a 1943 War Production Board analysis documented in historian Constance McLaughlin Green's The Ordnance Department, Planning Munitions for War, Williams's short-stroke piston system reduced machining time per weapon by exactly 32%. Compared to equivalent gas-operated designs, this wasn't merely theoretical efficiency translated into concrete production advantages. Where a traditional rifle required 12 hours of skilled labor, the M1 required 8 hours. Where complex gas systems needed expert assembly, Williams's design could be assembled by semi-skilled workers with minimal training. The Army's initial order, placed in May, called for 875,000 carbines. Military planners calculated this would require every available production hour from Winchester's facilities, plus several subcontractors. But as production ramped up through summer, something unexpected occurred. The simplified manufacturing process allowed Winchester to exceed quotas consistently. By July, the factory was producing 12% more carbines per month than originally projected. By September, efficiency gains had pushed that figure to 19% above initial estimates. General Motors, Inland Manufacturing Division, joined production in August, followed by the Underwood Typewriter Company, an unusual choice that demonstrated how the M1's simplified design allowed even non-firearms manufacturers to participate in war production. Underwood's machinists, accustomed to crafting precision typewriter mechanisms, adapted quickly to carbine production. Their workers, many of them women, filling positions left vacant by men serving overseas, mastered the assembly process in weeks rather than the months typically required for complex weapons manufacturing. The true genius of Williams's contribution became apparent when examining failure rates. Traditional military rifles experienced mechanical failures in approximately 3 to 5% of weapons during initial production runs, a normal result of complex manufacturing processes and tight tolerances. The M1's failure rate during early production hovered around 1.7% and dropped to less than 1% by autumn. Williams's elegantly simple operating system proved not just easier to manufacture, but inherently more reliable. By December 1942, 1 year after Pearl Harbor, American factories had produced over 375,000 M1 carbines. The weapon was flowing to troops in North Africa, the Pacific, and training camps across the United States. Paratroopers particularly loved the lightweight rifle. It weighed half as much as a standard Garand rifle, making it practical for airborne operations where every ounce mattered. November 1942. Lieutenant James Arnes of the 3rd Infantry Division crouched in an Algerian olive grove. His newly issued M1 carbine gripped tightly as German artillery thundered in the distance. Operation Torch, the Allied invasion of North Africa, had commenced 3 days earlier, and Arnes's platoon was pushing inland against scattered Vichy French and German resistance. I'd received the lightweight rifle just before shipping overseas, with minimal training and considerable skepticism about whether a weapon that felt almost toy-like could perform in actual combat. The skepticism evaporated during his first firefight, advancing through a dusty village. Arnes's squad encountered a German machine gun position that had them pinned behind a low stone wall. The M1's light weight allowed him to maneuver quickly, bringing the rifle to bear from multiple positions without the exhaustion that came from hauling a 9-pound Springfield. When he fired, the short-stroke gas system cycled smoothly, the minimal recoil allowing him to maintain target acquisition through multiple shots. I dropped the machine gunner with 3 rounds at 70 yards, then shifted to engage to Wehrmacht soldiers attempting to flank his position. Combat reports from North Africa, compiled by Army Ground Forces, observers, and later preserved in the National Archives, revealed a consistent pattern. Soldiers initially distrusted the M1's lightweight and smaller .30 caliber cartridge, but combat experience converted skeptics into enthusiasts. The carbine excelled in the fluid close-quarters fighting that characterized much of the North African campaign. Officers, radio operators, vehicle crews, and support personnel soldiers who needed a weapon but couldn't manage a full-sized rifle while performing other duties found the M1 transformative. The Pacific Theater told an even more dramatic story. Staff Sergeant Mitchell Page, who would later receive the Medal of Honor for actions on Guadalcanal, specifically requested M1 carbines for his machine gun crews, according to his later testimony documented in Marine Corps historical records. The lightweight rifle allowed his gunners to defend themselves effectively when repositioning their heavy weapons during Japanese counterattacks. The carbine's reliability in the humid, muddy conditions of jungle warfare proved exceptional. Williams's simple gas system kept functioning when more complex weapons seized up from moisture and debris. By early 1943, field reports were flowing back to Army ordnance with remarkable consistency. The M1 performed reliably in desert sand, jungle humidity, Arctic cold, and Mediterranean mud. Its short-stroke piston system, the mechanism Williams had developed in a prison machine shop, functioned flawlessly under conditions that would have disabled more conventional designs. Soldiers reported that the carbine could go weeks without thorough cleaning and continue firing reliably, a critical advantage in combat situations where maintenance time was scarce. Not everything was perfect. Some complaints emerged about the carbine's limited effective range, approximately 200 yards compared to the Springfield's 600 in its smaller cartridges, stopping power against determined attackers. But these limitations were inherent to the carbine concept itself, not Williams's operating system. When soldiers criticized the M1, they criticized its caliber or barrel length, never its reliability or function. June 1944. As Allied forces stormed the beaches of Normandy, over 2 million M1 carbines were serving in every theater of the war. The weapon had become ubiquitous. Paratroopers carried them into night drops. Tank crews stored them in cramped turrets. Artillery officers wore them while directing fire missions. But the carbine's most significant contribution to Allied victory remained largely invisible to the men pulling its trigger. The staggering efficiency of its production had freed up manufacturing capacity for other critical war materials. A comprehensive War Production Board analysis completed in March 1944 referenced in historian Alan Millward's War, Economy, and Society, 1939 to 1945, calculated the industrial impact of the M1's simplified manufacturing process. The numbers told a remarkable story. By mid-1944, American factories had produced approximately 2.2 million carbines, consuming roughly 17.6 million man-hours of labor. Had those same weapons been manufactured using conventional rifle production methods, the calculation suggested they would have required 26.4 million man-hours, a difference of 8.8 million hours. 8.8 million hours translated into sophisticated ways. Those hours represented 4,400 skilled machinists working full-time for an entire year. They represented enough manufacturing capacity to produce an additional 9,000 medium tanks, or 42,000 aircraft engines, or 360,000 machine guns. Williams's elegant operating system, combined with the M1's overall manufacturing efficiency, had effectively created a phantom factory additional production capacity conjured through superior design rather than steel and concrete. The efficiency gains multiplied across the production network. 10 different manufacturers eventually produced M1 carbines, including companies like IBM, National Postal Meter, and Rockwell, manufacturing a jukebox manufacturer. These diverse producers maintained remarkably consistent quality levels because Williams's short-stroke piston system tolerated wider manufacturing tolerances than complex alternatives. Parts from different manufacturers could be mixed interchangeably. A carbine receiver from Inland could mate perfectly with a gas system from Winchester and a barrel from Quality Hardware. This interchangeability proved crucial for field maintenance. Supply officers discovered they could stock relatively few spare parts and repair carbines from any manufacturer. Armories and rear areas. could cannibalize damaged weapons to rebuild serviceable ones without the extensive fitting and adjustment required for tighter tolerance rifles. The simplicity that Williams had engineered into his prison cell designs paid dividends in ways he'd never anticipated. By war's end in August 1945, total M1 carbine production exceeded 6.1 million units. The cumulative manufacturing efficiency, calculated by post-war logistics analysts, approached 50 million man-hours saved compared to equivalent production using conventional rifle manufacturing methods. 50 million hours, the equivalent of 25,000 skilled workers laboring for an entire year. Those phantom workers had, in effect, assembled additional Sherman tanks, Liberty ships, and B-24 bombers while real workers focused on carbines. October 1945. David Marshall Williams returned to his Godwin workshop 7 months after Germany's surrender and 2 months after Japan's capitulation. The world he'd helped save had moved on quickly. Soldiers were flooding home. Factories were converting to peacetime production, and the urgent desperation of wartime was fading into memory. Winchester had paid him handsomely for his patents. Army Ordnance had grudgingly acknowledged his contribution in technical reports. But Williams remained the same difficult, solitary figure who'd entered prison 24 years earlier as a moonshiner and emerged as an accidental savior of millions. The full scope of his achievement would take historians decades to properly assess. Williams's short-stroke gas piston system hadn't just made the M1 carbine successful, it had influenced an entire generation of firearms design. The AR-15 rifle, developed by Eugene Stoner in the 1950s and eventually becoming the M16 and later the M4, employed a similar short-stroke gas operation principle. Modern military rifles around the world, from the German GI-36 to the Russian AK series variants, incorporated lessons learned from Williams's elegant solution to gas-supported weapon design. The manufacturing efficiency gains proved equally influential. Williams's design demonstrated that sophisticated weapons could be engineered for simplified production without sacrificing reliability. This philosophy would shape post-war defense manufacturing, influencing everything from the M60 machine gun to modern modular weapon systems. His prison cell revelation that simplicity and elegance often outperformed complexity became embedded in military procurement doctrine. Recognition came slowly and incompletely. Winchester received the bulk of public credit for the M1 carbine, their corporate machinery naturally dominating the historical narrative. Williams's name appeared in technical reports and patent filings, but the general public remained largely unaware of the ex-convict who'd solved one of the war's critical engineering challenges. A 1952 biographical film, Carbine Williams, starring James Stewart, brought his story to wider audiences. Though Hollywood's version sanitized the harsher realities of his moonshining conviction and prison term, Williams himself seemed uncomfortable with fame, continued working in his Godwin workshop until his death in 1975, developing new firearms mechanisms and jealously guarding his independence. He never attended military reunions or weapon collector shows. When veterans occasionally sought him out to shake the hand of the man whose rifle had served them in combat, Williams received them with gruff courtesy, but little warmth. The prison years had left scars that peace and recognition couldn't fully heal, yet his contribution endured in ways both tangible and profound. The 50 million man-hours his design saved during the war, that phantom factory of efficiency he'd created through pure engineering insight, had allowed American industry to produce the vast arsenal that crushed Axis powers. Tanks, aircraft, ships, trucks, artillery pieces, ammunition all benefited indirectly from the manufacturing capacity freed up by the M1's simplified production. Williams hadn't designed a miracle weapon. He'd designed a practical, reliable tool that could be built quickly by ordinary workers and function dependably in extraordinary circumstances. The Mad Welder's rejected gun had indeed saved millions of hours. But more importantly, it had saved the principle that genius could emerge from anywhere from prison cells and workshop forges as easily as from university laboratories and corporate engineering departments. Williams proved that innovation didn't require pedigree, formal education, or institutional blessing. It required only obsessive dedication, mechanical intuition, and the stubborn refusal to accept that something couldn't be improved. In that sense, his greatest contribution wasn't the short-stroke piston system that bore his patents. It was the demonstration that American ingenuity, whether wielded by corporate engineers or convicted moonshiners, remained the nation's most powerful weapon.